Okay, so we're doing the gas laws, and here's the first part, which is all review, right? This is all review for the gas laws, standard temperature and pressure, and then P1V1 equals P2V2. Now what we're going to do is we're going to take this back to the ideal gas law. Even though the ideal gas law is down at the bottom of the page, we'll get there. But we should remember a little bit about the ideal gas law from last year. So if we take the ideal gas law and we make the ideal gas law PV equals nRT, and we take PV equals nRT, and then we divide out the nRT, and we take like a before and after picture, so we have P1V1 over N1RT1 equals P2V2 over N2RT2. Now you can see that P1V1 is multiplied. Look, P1V1 equals P2V2. So I can now take off the bottom, and there's Boyle's law. Right? So it comes from the ideal gas law. Now let's look at Charles' law. We'll just set this to the side for now, and we're going to look at Charles' law. So Charles' law is volume 1, temperature 1 is equal to volume 2, temperature, over temperature 2. Over temperature 2. All right? So now, if we go back over to our ideal gas law, we see, oh, look, if I cover this up here, I see V1 over T1. And then I see over here V2 over T2. Right? So these all relate back to the ideal gas law. So V1 over T1, V2 over T2. Now, my preference, just so we're clear, and I think I told you guys this last year, is always to keep things linear. So I prefer V1 T2 equals V2 T1. That's my preference, but you can do it either way you want, all right? Now, if we set this to a constant, what we get is you're going to put the constant in between, so you would get V1 over T1 equals constant equals V2 over T2, or you're going to get V1 T2 equals constant equals V2 T1. Now, let's do Avogadro's law. Again, Avogadro's law is going to come from the ideal gas law. Avogadro's law puts into play the volume and the amount. So, V1 and N1. Volume and amount. Or V1 and 2 equals V2 and 1. So if we add the constant in, we have V1 over N1 equals the constant. And then V2 over N2, right? Or V1 N2 equals constant equals V2 N1. Now, lastly, what we're going to do is we're going to use the combined gas law, which pays attention to P1, pressure, volume, and temperature. Pressure, volume, and temperature. So you should be able to write this one yourself. Now, before we go any further, I want to make one thing very clear. So let's move back up to the gas laws. And right here, when we're using gas laws, all temps must be what? In Kelvin. None of these formulas will work unless the temperatures are in Kelvin. Okay? All the temperatures must be in Kelvin. You have to change them to Kelvin. Kelvin is an additive scale, so you can't divide it out from Celsius, from Celsius, Kelvin and Celsius, all right? And so therefore, all of these T's must be in Kelvin. So for Charles' law, temperature in Kelvin. For the gas law, temperature in Kelvin. All right? Universal gas law. The universal gas law, R, is the ideal gas constant. Now, there are many of these, depending on the units that you use. We still use the same one. The one we use is 0.08206. And the units are Latham riding a camel. Liters ATM over Kelvin mole. That's the one we used last year and the year before, and that's still the one we use. Now, when you get to college, you'll learn a couple other ones, but this is the one that we still use. So we make sure all our numbers and our units match up with that, all right, while when we're doing any calculations. So our pressure, our P is equal to pressure, and that unit needs to be in ATM, and that's how we will cancel out our ATMs there. Our volume needs to be in liters. Our N is for amount, and that needs to be in moles. And our T, which is missing, needs to be in temperature. And that needs to be in Kelvin. Okay? Ready to do some practice problems? All right, oh gosh. What's your second page? Does it say example 1? Oh, yes, thank you, because mine does not. Mine says density of gas. Yours does not? But your second page says this, please? Okay, okay, good. Okay, so I just stapled mine in the wrong order. Okay, good. All right, this is your second page, right? Page 2? Okay, good. All right, good. All right, example 1. A sample of a gas at 15 degrees Celsius and 1 ATM has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees Celsius and 1 ATM? So, first of all, not all of these formulas need all of these, like all of these problems need every formula. So what you're going to do is you're going to say, okay, so I have a temperature here and a temperature here. I have a pressure here and a pressure here, right? And I have a volume here, and I want to find another volume. So my pressures are the same. So I don't need to concern myself with those pressures. So now I'm looking at temperature and volume. all right? Temperature and volume. Do I have a temperature and volume formula? I do. It's Charles' law. So I look and see, and I have a temperature and volume formula. So the formula I will be using is volume 1, temperature 2 equals volume 2, temperature 1. So now I lay everything out. My temperature 1 is equal to 15 degrees Celsius. My volume 1 is equal to 2.58 liters. My temperature 2 is equal to 38 degrees Celsius. My volume 2 is what I'm looking for. Everybody okay? So now I need to put my temperatures into Kelvin. So 15 plus 273 is equal to 288. $38 plus 273, 311. And now I'm ready to plug in. All right, so 2.58 liters. Most common problem is not switching your temperatures. 388 liters. Whoops, sorry. V1. Yeah, V1, T2. Volume 1, 2.58 liters. T2, 388 Kelvin. Sorry, Kelvin. What? Oh, I'm sorry. 311 is correct. I have it on my calculator. I just wrote it down wrong. 311 Kelvin. Yep. Okay, is equal to V1, right? V2, T1, 288, right? Kelvin. Yes? Okay. So now I solve V2 is equal to I get 3 digits, right? So I get 279. 2.79. Yes? All right. Next problem. Suppose we have 12.2 liters, so that's a volume, containing 0.50 moles of oxygen at a pressure of 1 atm and a temperature of 25 degrees Celsius. If all this O2 were converted to ozone at the same temperature and pressure, what would the volume of the ozone be? So we're going to need to do this as an equation first. All right. So the first thing we're going to need to do is we're going to take O2, gas, and we're going to need to convert this to O3, gas. And then we're going to need to balance this. And so what we have here is 5 moles, 0.5 moles of O2. And we're going to need to know how many moles we get in the end of this. Okay? Do stoichiometry. So we end up with 0.33 moles of O3. The question is, what would the volume be? So now what we know is we started with this volume. Excuse me. So we have volume, we have moles, now we have moles, and we have temperature. And the question is, what is the volume? So we have we have T1, N1, and V1, and P1. You with me? What we want to know is V2. So let's lay it all out, right? You with me? So let's lay it all out. So P1, 1 atm. V2, V1, 12.2. N1, T1, okay, P2, 1 atm. V2 is what we're looking for. N2, 0.33. And T2, well, the temperature isn't changing because it says the same temperature and pressure. So if the temperature is remaining the same, we don't need it. Everybody with me? The pressure is remaining the same, so we don't need it. So we're working with Avogadro's rule, which is volume and moles. Everybody okay? So I go back and I look, Avogadro's law. Everybody see how this is working? Here it is, Avogadro's rule, V1 over N1, or V1 N2. Okay? So Avogadro's rule, V1 N2, or V2 N1. And now I can plug everything in. How are we doing? We okay? Should we do one more? We have 5 minutes, 3 minutes, 2 minutes. Let's stop.